In this video, we're going to talk about general types of characterization that we can do on polymers. And I'll try to highlight the characterization techniques that we are using in this third lab, the Polymers Characterization Lab, and then others that can be useful additions. All right, so polymer characterization, there's a lot of techniques that you will see for other classes of materials like metals and ceramics, but there's also some that are kind of fundamentally different, and we'll kind of go through. So I've kind of broken them out into different classes. And so you see that here we have thermal, and then we have physical properties, and then we have molecular and crystalline structure. We have mechanical properties and surface and morphology properties. So I've kind of grouped it up into this, and that's just to kind of classify each of the different types. So let's look at the first one first. So thermal properties. This is something that is done in all the classes of materials, but DSC in particular, and some of these other techniques are used extensively in polymers, and this is something that we haven't yet done in our curriculum in a physical manner. So DSC, or differential scanning calorimetry, this is something that we're doing in the lab right now, and it measures the power difference between our reference sample and our actual sample to be able to give us information about thermal events, such as the glass transition temperature of a polymer, the melting temperature, crystallization, any other phase transformations, and it gives us those temperatures, but also gives us enthalpies of those events. And so there's a lot of power and a lot of properties that come from this technique. TGA, or thermal gravimetric analysis, is another. This measures the mass as a function of temperature. So a lot of these names are named after kind of what they do. And so this measures mass as we heat up, typically, something. And so this can give us some information about phase transformations, degradation, if there's any absorption or desorption events, so if there's water in the structure, and also oxidation or reduction reactions, because you're measuring the mass. There's also differential thermal analysis, which is similar to DSC, gives similar information. There's also TMA, which is thermal mechanical, and so this gives you some changes in the mechanical properties. It looks at dimensions, and so this is important if you're after the coefficient of thermal expansion, CTE, or other forms of what you might have seen thermal coefficient as. So that's an important technique. So basically it takes the standard size and it looks at the changes in the dimensions with temperature. So thermal is a kind of a class that we haven't yet looked at up until this lab. And so that's the kind of DSC is the big new technique that we're using in this. And again, it's really important for polymers, but can also be used in metal, ceramics. It doesn't matter. All right, so next, physical properties. A lot of these are things that we might not think about or just kind of gloss over, but they can still be really important. Density, I'm asking that you characterize the density of our samples. So this can be easy as taking the dimensions and mass and calculating density. In some cases, Archimedes method can be used, but it's a very straightforward, but density is really important. The general kind of rule for polymers is that their density is around the density of water, so 1 gram per centimeter cubed, with variations. So as you might have seen before, some polymers will float on water, and so therefore their density is lower, and then others will sink, and so their density is slightly higher. But the 1 gram per centimeter cube is a pretty good reference point for that. Color. So I ask everybody to sort of make general observations about their polymers. So color can be part of the intrinsic nature of our polymers, but you can also add additives to affect the color. And so you have to be a little bit cautious when the color is involved, but the color can tell you in certain cases a lot of information about the polymer. Opacity or how transparent something is. This is really important. This is often something that changes from sample to sample, and it's really heavily connected to crystallinity, so how crystalline something is, and also the defects in that sample. And so this is a useful characteristic to look at when you're looking at your samples. Again, here, some caution has to be paid, because if there is additives, solid particles, so forth, that can affect the transparency as well. Solubility, this is something that we don't typically look at for metals and ceramics unless we're talking about maybe etching or something like that. But in polymers, solubility is really crucial for a lot of the applications, and also compatibility, when and where we can use these polymers. And so solubility is useful in those cases. Solubility here, we're not necessarily just talking about water. Most polymers are not soluble in water, but we're typically talking organic solvents, toluene, acetone. I'm blanking on a couple more, but there's a list there. So these solubilities for polymers can typically be found on a lot of chemical companies' websites, particularly if you're dealing with tubing and things like that, because you want to know that the chemicals that you're passing through a polymer tube are compatible with that material. So this is something that we can readily find out and compare. A couple other ones I put there based on a joke a student made a couple of years ago. Smell and taste. While there are some arguments that you could identify polymers based on that, that's a no for this lab. So stick to the others on that. All right, so next, molecular and crystalline structures. So just structure in general. We typically think about crystal structures when we talk about metals and ceramics. But when we get to polymers, oftentimes the molecular structure is just as or much more important. And so these are probably a lot of techniques that you might not be familiar with when you're talking about metals and ceramics. But these are the ones that really sort of differentiate those characterizations from polymers research. And so NMR, or nuclear magnetic resonance spectroscopy, is a really powerful tool that gives different molecular and functional groups in the structure. So it can really tell you what you have there. IR, or infrared spectroscopy, gives you different molecular bonds as well. UV vis, or ultraviolet visible spectroscopy, is similar to IR in those ways. Raman can give you similar kind of vibrational information, so it's a lot of molecular bonds that we have. Mass spec, or mass spectrometry, looks at a different ionized species, so it can give you the chemical makeup, so what you have in there, and so that's a really powerful tool. There is gas permeation chromatography, GPS. This can give you molecular weight, and so that's a big one that comes up. Molecular weight has a huge influence on the various properties, so we can have the same polymer, but a different molecular weight can give us different properties. That's unlike what we see with metals, because the molecular structure doesn't change. And then we have other techniques, diffraction techniques. XRD can be used for crystalline polymers, and then you have wax or SAX, which are wide angle and short angle X-ray spectroscopy, which can be used for more amorphous structures to give us some of the closer, shorter range order that we have in these structures. And so that's more commonly used in polymers. So there's a lot of new techniques that we probably haven't used, and this is where some of our limitations in our lab come up, because we would love to do things like NMR, but those are a little harder for us to do. Next, mechanical properties. A lot of these are things that you've already done for other materials. So tensile testing, impact, hardness, all of those things can give us useful information about polymers, the mechanical properties, and so forth. So those are all things you're used to. There's differences when you talk about the viscoelastic properties of polymers that come in those tests. But the other one is rheology. So when things are more liquid-like, studying the viscous flow and viscous behavior of those materials. So a lot of the mechanical properties can also be expanded into viscoelastic properties, and so those get away from traditional metals techniques. And then lastly, these are a lot of things that we're probably familiar with. SEM, TEM can give you information about the surface or the roughness of a surface. AFM can do the same thing. But also things like contact angle and adhesion properties. Those can give you information about the hydrophobicity, how slick the surface is, and so forth. And these are fairly common in polymers and also surface techniques. So, again, this is just a wide array of things that we can look at. The big one that we're adding to your sort of repertoire of techniques is going to be DSC. So we're doing DSC. We're also looking at the density. Solubility is an option for additional testing. You're looking at color, opacity, again, no smell and taste. Here in the molecular range, we're not doing as much, but we are doing X-ray diffractometry. We're able to do that very easily for us. Tensile testing, hardness testing is another additional test that you can do. We have more limited options for rheology. And then additionally, things like contact angle and adhesion, looking at the surface properties, these are things that we can do with additional testing if your samples dictate that. So again, just wanted to give you a broad array of characterization tools that are typical in polymers and what they sort of give you in a general sense. So hopefully if you ever need those additional testings, then we can do that.